Hello, myself Professor C.D. Kadhane from K.K. Wagh Institute of Engineering Education and Research, Nashik. Our institute 8 branches have been accredited by NBA, New Delhi, and our institute received a platinum category under CII survey. Now in today's lecture we are going to study the design of roof trusses. In design of roof trusses we are going to learn how to find out loads at different panel points of roof truss. So let us learn about first the lecture outline. So in lecture outline we are going to see first is introduction to steel structure and components, types of roof trusses, application of roof truss for different span lengths. Then we are going to study the different concepts such as pitch, rise of steel roof truss, then spacing of purlin and location of purlins. Then we are going to study the procedure for calculation of loads on truss. So first we will think about how to calculate the different geometrical lengths of roof truss, that is geometrical calculations of roof truss. Then we will learn how to find out dead load, panel point, full panel point or half panel point dead load by using IS 875, that is part 1. Then we will study how to calculate live load by using IS 875 part 2, and at last the wind load calculation by using IS 875 part 3. Now this is the 3D view of a industrial or a steel roof structure. In this case of steel roof structure, this is a span of a truss. This is actually called as a bend. Bend consists of column, then roof truss and another column. So this is called as a bend. So in this case, this portion, top portion, sloping portions is called as top chord, whereas the bottom of the main tie is called as bottom chord. So here all these members running parallel to the length of the structure on the top of roof trusses are called as purlins. So purlins are parallel to the length of structure. Similarly, on the wall cladding there are horizontal members, and these horizontal members act as a supporting for the wall panels, and they are called as wall girts. Here this is a roof truss. Then here there is an opening provided to the industrial structure, where these are the bracing, these are, you can say, cross bracing, and these are longitudinal bracings. So whatever bracing provided at the top are called as top bracing, whereas these are called as longitudinal bracings. So this is here in this case, this is a vertical column and a roof truss. Similarly in plan, if you can look at the bracings provided, which is at the periphery of structure and which is provided at the tie level or bottom chord level. So this function of this providing this bottom chord bracing is to keep complete structure intact at one place whenever large wind pressure is acting on the structure. Now let us study different types of roof trusses. This is a king post roof truss, then pitched Pratt truss, pitched hoe truss, fan truss, then this is a queen post, inverted queen post, then this is a pitched pink truss, this is a subdivided panel truss, then this is a parallel chord Warren truss, this is a parallel chord Pratt truss, parallel chord hoe truss, parallel chord with diamond or K-type wave. These are diamond and K-type wave, and this is a trapezoidal truss. Similarly, there are different types of trusses in the shape of bowstring trusses, mansard truss, then this is a virendial girder, then this is scissors truss, then this is a cambered truss. Here bottom portion or bottom tie portion is little bit cambered one, uplifted upward in a upward direction, so this is called as cambered truss. Then this is north light truss, and this is a pitched roof with monitors. Now Whenever span changes, then we have to select different trusses as per the requirement of structure. So in case of spans up to 8 meter, we can use a king post truss. Then for spans up to 10 meter, we can use a queen post truss. Then in case of span ranging from 6 meter to 30 meter, we can use a hoe truss. Similarly, in case of spans varying from 6 meter to 100 meter, we can use a Pratt truss, or you can use a modified Pratt truss. Similarly, in case of spans, actually this is not the correct value provided here. Spans ranging from 10 to 20 meter, we can use a Fink or French roof truss. Here, if two members, extra members are provided at this point connecting to the top chord member, then it's called as a fan truss. But in this case, this is a Fink or French truss. Similarly, for spans up to 20 meter to 30 meter, compound French roof truss can be selected or can be chosen. Similarly, cambered French roof truss for the span ranging from 20 meter to 30 meter. Similarly, this one is a fan truss and it can be employed for spans ranging from 10 to 50 meter. This is a north light roof truss and can be employed for spans from 8 meter to 10 meter. This is a quadrangular truss and this is a truss used for large span. So let us study about the pitch of trusses. So what is pitch? Pitch is actually a ratio of height of a truss to its span. And due to this pitch, it gives idea for the drainage of a rainwater. So for different type of structure as per their location as well as width and length of structure, a drainage requirement will vary similarly depending on type of a sheet, GI, whether it is a GI sheet, galvanized iron sheet or asbestos sheet, again a pitch will vary. So for corrugated GI sheet, pitch of 1/3 to 1/6 can be chosen. For corrugated AC sheets, pitch of 1/6 to 1/12 can be chosen. Similarly, other type of roof covering and their pitches are mentioned. So whenever there is a snow load, a pitch of 1/4 is economical. When there is no snow load, adopt lower pitches up to 1/6. Now let us learn about a depth of truss. Actually, here different types of trusses or different types of beam elements or open web elements, their approximate depth, approximate span and typical spans are mentioned. So here for Fink truss, the approximate depth is taken as L by 5 to L by 6. Approximate span for Fink truss is 10 to 18. Typical span is 50 meter. Similarly for hoe or Pratt truss or fan truss, approximate depth is L by 5 to L by 6 and their span ranging between value of 10 meter to 50 meter, typical span 12 meter. Similarly, other type of trusses or girders, the values are mentioned in the table. Now, let us learn about what is the spacing of purlins. So actually, there are two ways of keeping the purlin on the top chord of a roof truss. We can keep all the purlin at the exactly joints of a roof truss so that there will be no bending moment in a top chord members. So whenever purlins are kept exactly at the joints of roof truss, only axial loads are produced in the interrupter. But when the requirement is such that we have to keep all these purlins at the joint as well as in between the two joints, then the Prince Raptor is subjected to axial compression as well as bending moment. That means Prince Raptor should be designed as a beam column. See, that beam column which is a complete length of Prince Raptor can be considered as a continuous beam. So it can be treated as for analysis purpose as a continuous beam. So for corrugated GI sheets, spans ranging from 1.5 to 2 meter can be considered or can be selected, and for corrugated AC sheets 1.4 meter for 6 mm thick sheets and 1.6 meter for 7 mm thick sheets are chosen. So these are the spacing for GI sheet as well as AC sheets. Now let us learn about what are the design steps for calculation of load for design of roof truss. So first step is geometrical calculation for truss. In geometrical calculation of roof truss, first we have to select a truss from the given dimension of a structure or span of a structure. Similarly, select a pitch of truss, calculate rise of truss, then slope of a truss. Then third step is calculate length of principal rupture, spacing of purlins, draw neat sketch showing complete truss with location of purlins. So after calculating all these lengths, we have to draw a neat sketch showing the location of purlins and truss members. Then afterwards, we have to find out you have to find out the plan area and sloping area of one truss. So finding plan area of roof truss, we have to consider span multiplied by the spacing of truss. Whereas if you want to find a sloping area of one truss, then length of principal 2 into length of principal rupture into spacing of truss will be considered. So for finding a dead load on a roof truss, we have to consider a IS code IS 875 part 1. But let us learn what are the different types of codes or how many parts are there in case of IS 875. So for 875, part 1 is a dead load, part 2 is imposed loads, part 3 is a wind loads, part 4 is snow loads, and part 5 is a special loads and combinations. So here IS 875 part 1 dead loads, that code face sheet scanned copy is attached here. Similarly, enlarged view of a title of a IS 875 part 1 is mentioned here. So whenever you want to find out a sulfate of a GI sheets or other type of sheets, you can refer IS 875 part 1 table 1 serial number 39 and page number 10. So let us study the second step, that is the calculation of a dead load. So for calculation of dead load, we have to consider self-weight of sheets. Generally, GI sheets should be assumed. In modern day, all structures in all structures, GI sheets or galvanized iron sheets are used. Then similarly consider weight of bracing, weight of fixtures and fasteners, self-weight of truss, and self-weight of purlin. So self-weight of GI sheet is taken as 131 Newton per meter square for 1.6 mm thick GI sheets. Similarly, for weight of bracing, we can consider value of around 10 to 15 Newton per mm square. Then weight of fixtures and fastener, you can consider 10 Newton per mm square meter square. Then self-weight of root truss is equal to span upon 3 plus pi whole multiplied by 10, which will give us a weight of truss. It will give us weight of truss in Newton per meter square. Similarly, we can add in this self weights the weight of a purlin. Here, weight of a purlin, initially you can assume a average weight of a purlin for that particular panel, and from that you can find out, or you can find out total weight of all purlins for a plan area, and then total weight divided by total plan area will give us value Newton per meter. So we have to add all these values, intensity of a dead load, we have to add them, and that will give us total dead load intensity. Please convert that intensity of dead load in kilonewton per meter square. Now we have to calculate total dead load on a single roof truss, and that is equal to plan area of a truss into dead load intensity per meter square, which is found out in the previous step. Here I will again explain what is meant by plan area. Plan area is a multiplication of span of truss and spacing of a truss. Now after that we have to find out or calculate full panel point load. After finding total dead load on a single roof truss, so consider that total dead load on a single truss divided by number of full panel points of a single truss. So if we take example of pink or French truss, then there are 8 full panel point load. Therefore this total dead load on a single truss divided by 8 will give us value for full panel point dead load. And from that full panel point, that is for dead load, we have to calculate half panel point dead load. and that is equal to this value found out in the previous step divided by 2, that is full panel point dead load or full panel point load divided by 2. After finding all these full panel point loads and half panel point load, draw a neat sketch of a given truss and show all full panel point load and half panel point loads. Now let us learn now the next load, that is the imposed load. So IS 875 part 2 provides us information regarding imposed loads or live loads. So this is a scanned face sheet of a 875 part 2, and this is enlarged heading or enlarged title of a IS 875 part 2. Now what is meant by imposed or live loads? Let us learn about it. So these are greatest load that probably will be produced by intended use or occupancy. So these live loads or imposed loads includes the weight of movable partitions, impact and vibration, which includes load applied suddenly, then dust load. Now imposed or live loads, and these imposed and live loads will vary as per the type of occupancy or function of a building. So depending on group of building, so there are different types of buildings or group of buildings. There are assembly, business, office, educational, industrial, institutional, mercantile, residential dwelling and storage. So as the building occupancy changes, function changes, then their intensity or live load will change. So here this table number 1 gives us idea regarding how much UDL we must consider for different types of structures. In this also mercantile, if you think about mercantile buildings or industrial buildings, and if you compare with the residential building, the live load is higher as compared to the residential building. So industrial building live load also, light duty building 5 kN per meter square is taken, medium duty building 7 kN per meter square, and heavy duty building 10 kN per meter square, whereas these buildings are work areas with machinery or equipments. Now whenever we want to calculate a live load on various types of roofs, so we have to refer table number 2 of IS 875 part 2. Here in serial number 1, first part is a flat sloping or curved roof which slopes up to and including 10 degrees. So this is applicable for flat roofs and a slope of a roof less than 10 degrees. If access is provided on a roof, then consider UDL, uniform distributed load, that is imposed load 1.5 kN per meter square. If access is not provided on the roof except for the maintenance, then consider a lower load, that is 0.75 kN per meter square. Whereas here minimum imposed load measured on plan is also mentioned here. So this is the minimum imposed load should be considered for the design of roof. In second point, which is very important for us in case of design of roof trusses of industrial structures or shades, this point will be very useful for us. So in many times, or you can say every time, the roof truss slope of the industrial building will always be greater than 10 degrees. So if the roof slope is greater than 10 degrees, then the value of live load will be equal to 0.75 minus 0.02 in bracket theta minus 10 degree. But the minimum value of live load for slope greater than 10 degrees should be 0.4 kN per meter square. Similarly, this third point is for curved roof with slope of line obtained by joining springing point to the crown with the horizontal greater than 10 degrees. So this is a formula mentioned here for curved roof. Again, for curved roof also, the minimum live load of 0.4 kN per meter square should be considered if calculated live load is less than this 0.4 kN per meter square. Now, whenever we are to consider a slope as per the pitch, so these are the guidelines given in the table. If these are the values of pitches, then these are the values of angles. So in case of corrugated GI sheets, pitch is taken between 1/6 to 1/3, and the best value is 1/5 to 1/4. That is span upon 5 to span upon 4 will be the value of a pitch for GI sheets. The slope of GI corrugated roof is selected between, that is 18 degree to 33 degree. That is, this 1/6 is 18 degree and 1/3 is 33 degree. That means for GI sheet, a slope ranging from 18 to 33 degree, that much value should be considered in case of slope. Now let us learn about live load calculation. So live load is equal to 0.75 minus 0.02 in bracket theta minus 10 bracket computed kilonewton per meter square. If you want to find out this value in Newton per meter square, then our formula will be 750 minus 20 in bracket theta minus 10 bracket computed Newton per meter square. Now, whatever live load found out in this step must be greater than, it should be greater than equal to 400 Newton per meter square. Actually, this is not the condition. This live load should not be less than 400 Newton per meter square. Whatever live load calculated on actual structure should not be less than 400 Newton per meter square. If this value is less than 400 Newton per meter square, then we have to compulsorily consider 400 Newton per meter square as our design live load. But if live load calculated by this step is more than 400 Newton per meter square, consider that larger value for the design of roof truss. So if value of live load less than 400 Newton per meter square, then consider live load is equal to 400 Newton per meter square. Now, while considering live load for a truss, it should be taken as 2/3 the live load intensity per meter square. So now calculation of total, actually here there is mistake, calculation of total live load on a single roof truss is equal to plan area of truss into live load intensity on a truss, that is found out in the previous step. Again, plan area is nothing but the span of truss into spacing of truss. Now after finding out the total live load on a plan area, next step is calculation of full panel point live load, that is for intermediate panel points. Therefore, total live load on a single truss divided by number of full panel points of a single truss. This will give us a total live load at an intermediate panel, that is a full panel point load. Similarly, calculation of half panel point load, that will be equal to full panel point load divided by 2. After that, you have to draw neat sketch of roof truss showing all panel point live loads on a given truss. Now let us learn about the wind load calculations. Before wind load calculation, we have to study the IS 875 part 3, and that is the latest code, that is 2015. So here this is a scanned face sheet or front sheet of IS code 875 part 3 1987, and this is a map of India showing different wind speeds or wind speed zones in India. Here whatever yellow color is mentioned, that means our Nasik is lying, Nasik and middle India, some part of east part of Gujarat, then majority part of Maharashtra, then south part of Madhya Pradesh, then part of Bihar, part of Orissa, all these are part of Andhra Pradesh, part of Chhattisgarh, then part of Karnataka, all these parts are shown by yellow color. That means the wind speed in this region is 39, whereas highest wind speed is available in the eastern coastal area of Indian Ocean. Similarly, Gujarat coastal area, the wind speed is highest. Similarly, in the northeastern states, the wind speed is highest, which is shown by a red color. Now, for design wind speed, finding design wind speed, similarly design wind pressure, IS 875 part 3 gives a clear-cut idea regarding to find out design wind speed as well as design wind pressure. So here the design wind speed Vz, it can be found out by multiplying Vb into K1 into K2 into K3 into K4. whereas Vz is a designed wind speed at height z in meter per second. K1 is a probability factor, it is also called as a risk coefficient. K2 is a terrain roughness and height factor. K3 topography factor. K4 importance factor for the cyclonic region. You can refer IS 875 part 3 for detailed study of this theoretical background as well as the mathematical formula given there. Similarly, for designed wind pressure, the formula is mentioned in the IS code, that is Pz is equal to 0.6 Vz square, where Pz is equal to wind pressure at height z in Newton per meter square and Vz is equal to designed wind speed at height z in meter per second. Now the designed wind pressure Pd can be obtained as, that is Pd is equal to Kd into Ka into Kc into Pz, where Kd is equal to wind directionality factor, Ka area averaging factor and Kc combination factors. And for combination factor you have to refer section 73313. The value of Pd in above formula, however, shall not be taken as less than 0.7 Pz. That is very important. So for detailed study of all these parameters or all these formulae in IS 875 part 3, you have to refer actual copy of the IS 875 part 3. Now for sake of understanding, we are going to consider one example for calculation of wind load. So let us consider size of industrial structure 16 meter by 14 meter with a fink roof truss as shown in figure, located on a plain terrain near Nashik. Let us consider spacing of trusses as 8 meter, rise 1/4 into 16, that is equal to 4 meter, building height 10 meter, consider terrain category as a 3 and structure of class B. So this is a sketch which is provided for a pink or a French truss. Span is 16 meter and the spacing between the purlin will be 2.235. This is a rise, that is 4 meter. Now let us consider the first formula, that is Vz. So let us find out wind speed Vz is equal to Vb into K1, K2, K3, K4, where Vb is a basic wind speed and for Nashik it is 39 meter per second. So this value 39 meter per second is provided at the end of IS 875 part 3. So from IS code 875 part 3, K1 value is equal to 1, K2 terrain roughness and height factor is equal to 0.89, K3 is equal to 1, K4 is equal to importance factor for cyclone region and that is also equal to 1. Therefore design wind speed Vz is equal to this 39 into 1 into 0.89 into 1 into 1 equal to 34.71 meter per second. Now let us find out Pz. So Pz is equal to 0.6 into Vz square. So P in this case, in our example, Pz is equal to 0.6 into 34.71 bracket square. That comes out to be 722.87 Newton per meter square. Now let us find out designed wind pressure. That is Pd is equal to Kd into Ka into Kc into Pz. So Kd is equal to wind directionality factor, which is equal to 0.9, Ka area averaging factor 0.8, Kc combination factor 0.9. All these three factors can be referred from IS 875 part 2. Therefore Pd is equal to 0.9 into 0.8 into 0.9 into 722.87 and the answer is 468.42 Newton per meter square. So in this way we have calculated the designed wind pressure acting on a structure per meter square. Now after finding out a designed wind pressure for a particular location in a country, so in our case, in our example, we have considered Nashik as a location, but if location changes, whether it's Ahmedabad or whether it is Calcutta, Delhi, Chennai or anywhere in India, accordingly we have to choose a different wind pressures, and as per that wind pressure, location of structure, size of structure, type of a ground, type of a terrain, we have to calculate the designed wind pressure. So in our case the structure or industrial structure having a span of 16 meter and height is 10 meter. So if you divide H upon W, that is 10 upon 16, that comes out to be 0.62, and that is case number 2. This is case number 2. That means when our H upon W value is lying between 1/2 to 3/2, then we have to consider this one. So slope of our industrial structure or roof truss is 26 degrees. So here between 20 to 30 degrees we have to interpolate all these values. Here wind angle theta is mentioned, that means 0, means when wind is blowing perpendicular to ridge, we have to consider this EF. We have to consider EF value and GH value. When wind is blowing parallel to ridge, you have to consider EG value and FH values. So by interpolating values between 20 degree, 30 degree and 26 degree, we have to find out all these values, and we have to enter these values in a table which is mentioned in the next slide. Now here again I will explain. We have to find out first ratio H upon W. H is nothing but a height of a structure up to use level, divided by W is the span of a structure. So in our example, the height is 10, span is 16, therefore 10 upon 16 is coming 0.625, and therefore we have to consider second column of a wind pressure from IS 875 part 2. So here we have prepared a table mentioning wind angle here, wind angle. So here this wind angle is mentioned, and actual slope of our truss is 26.56. Here different cases, that is windward and leeward cases, are mentioned. So for 0 degree angle, that means wind is blowing perpendicular to the ridge. In that case, windward direction we are getting minus 0.37 and leeward direction minus 0.5. And internal pressure we have to consider. So this internal pressure, in this case we have assumed internal pressure as a plus minus 0.2, that is a normal permeable structure. Whenever there is a medium permeable structure, this value is taken as plus minus 0.5. When it's a high permeable structure, then these two values are considered as a 0.7. So here CP, that is external wind pressure minus internal wind pressure, the windward direction calculated, leeward direction calculated. Similarly wind loads, windward direction calculated and leeward direction calculated. So from this CPE minus CPI, if you observe these two columns carefully, then you will find that this value, that is for ridge angle 90 degree, that is when wind is blowing parallel to the ridge, and windward direction, the coefficient minus 1 is highest out of all these coefficients. That means minus 1 and minus 0.93 gives us maximum value of wind forces in windward direction as well as leeward direction. So windward direction maximum value of force is 33.516 kN and leeward direction 31.203, and these values actually should be negative because this signs here are negative. That means both the forces are acting away from the truss. That means truss is subjected to suction wind load. So that is the end of design of roof truss as well as calculation of dead loads, live loads, wind loads, and we also learned in today's lecture how to use IS 875 part 1, IS 875 part 2 and IS 875 part 3. For detailed calculations during our numericals or example based on design of structure, we will learn all these IS codes one by one so that you will grasp all the concepts regarding finding all loads on a structure. So I think that is the end of today's lecture. If you have any questions or any doubt in your mind, you can raise your hands, you can raise your query so that I can answer these questions. Thank you very much for listening this lecture. Thank you once again. Stay at home and stay safe. Thank you. एवढं असतं. काय कळलं का साहेब? पोरांना डेंजर आहे. किती मिनिटं